Assalamualaikum warahmatullahi wabarakatuh. Today I'm going to give a lecture on safety working in microelectronic or semiconductor clean room. So I divide the lecture into two parts. So the first part is about clean room itself and clean room and contamination control. And the second part is about safety procedure, where I will explain in detail about the safety working in fabrication laboratories. So first, look at what is clean room and contamination control. So one of the reasons why we need a clean environment or clean room or clean lab is to free from contamination. So the type of contamination, there are three types of contamination. One is particulate or inorganic dust, such as metallic, silicon, glass or quartz, and etc. And organic dust, such as dry skin, hair, clothing fibers, makeup, bacteria, and etc. Another one is a film contamination, is the residue from oil, grease, or fingerprint, or incomplete etch. A solvent residue from acetone or IPA and everything. Photoresist developer residue, inadequate rinsing, or water stain. So that is film contamination. And another type of film contamination is oxide, grown by thermal. Oxide layer can be grown by thermal or chemical or electrochemical process. So the third type of contamination is atomic contamination. Absorb and absorb atom of ion in or on the film or substrate, such as sodium, calcium, aurium, copper, ferron, and so on. So what is the source of contamination? In clean room, we have two sources of contamination. One is from human and another one is from machine. Of course, the material also contribute to the contamination, but that one is the main one is human and machine for particle-free environment. So from human, human is cause most of contamination from dirt, oil, etc. tracked into lab and shoes sole. Body continuously exfoliate skin, replace hair, widespread use of makeup, perfume, hair gel, and etc. So this will spread throughout lab by central air conditioning. So use of mechanical tweezers, scratch and chip wafer edge and surface. This is from human. Machine, abrasion during automated wafer handling, mechanical mechanism, wear and lubrication, aging plastic and rubber part. So this can contribute to contamination in the clean room. So what is problem that we can have if we have contamination? So we call it contamination induced problem. One is to the device that we fabricate, and another one on the process when we do fabrication. So first, mobile ion. Mobile ion exists in oxide layer. So this oxide ion, normally positive charge, can change the electric field and voltage at the silicon surface, mostly an issue for MOSFET transistor, but also exploited for anodic wafer bonding in MEMS fabrication. So another one is impurity in silicon. So impurity act as a recombination center for electron hole pair and impact carrier concentration and also distribution. So if contamination happen during the process, So it will create the electron hole pair center. Another one is a particle on surface or in the release action. So this will create numerous problems during photolithography. It can jam the micromechanical structure. So we will discuss later on the photolithography. And fourth is unintentional film between layers. So the layers that can create open circuit or short circuit between layers. So impede adhesion between film and release edge. So now, what is clean room? The definition of clean room. So a clean room is a man-made environment that has much lower particle count than the normal environment. So the first clean room were built for hospital surgery room to control the airborne bacterial contamination which is responsible for post-surgery infection. And soon after semiconductor industry developed, engineers or a device engineer or fabrication engineer realized that the importance of contamination control and adopted cleanroom technology in transistors and IC fabrication. So cleanroom is a work area in which the air quality, temperature and humidity are highly regulated in order to protect sensitive equipment from contamination. So cleanroom are important features in the production of silicon chip, hard disk drive and other technologies such as satellite. So the air in cleanroom is repeatedly filtered to remove dust particles and other impurities that can damage the production of highly sensitive technology. So the standard definition of cleanroom classification can be metric unit and also English unit. So in English unit, for example, class 10 cleanroom is defined as having 10 particles with diameter larger than 0.5 micron per cubic foot. And class 1 must achieve less than 1 particle with diameter larger than 0.5 micron per cubic foot. A fab for making IC chip with a minimum features of 0.25 micron need a class 1 cleanroom to achieve an acceptable yield. So cleanroom contain plastic wall and ceiling, external lighting, and there is a continuous influx of clean and dust-free air. So the room should be cleaned daily to prevent contamination. So this is very general about clean room. So many different industries require the use of clean room, such as medical facilities, integrated circuit manufacturer, and dairy farm are just a few, including other industry such as satellite, everything. So it is vital that construction of clean room includes strict control of environment condition in order to ensure a quality room. So the environmental condition in a clean room are controlled by particle enclosure during installation of the wall, floor, ceiling, and media. Effect of a particulate on the structure that we're going to fabricate. So as you can see from the slide, the defect on microcircuit due to particle on mask. We want to make a pattern, so we have to use optical mask and transport to the wafer. So if we do this not in the clean environment, so particle will settle on mass and will be transferred on the device that we're going to fabricate. As you can see from the diagram, two particles will make the line short circuit after we develop and process. So this is the effect that will damage the device that we fabricate, and the device will not work. So this slide just to show you the same thing, the effect of particle on the device when we fabricate it not in a proper clean room. So you can see the structure where you see the particle will settle on the structure and we make the structure short circuit or open circuits. So this is what we don't want. So particles, our atmosphere contains many floating particles like microorganisms, fibers, skin flakes, carbon, metal, and also non-metal. So air contains millions of different sized particles, which cannot be seen by a naked eye. The particle that you can see by your naked eye is already very big, and that one you can easily remove. But the particle size smaller than that, you cannot see, even though you feel that you are already in clean environment. So that's why we need a proper filter to clean the environment. Comparison of particle sizes. Well, sometimes we cannot imagine how small is the particle. When we say it's a 1 micron particle size, is how small is the particle. So we compare with the object that we can see. We compare with human hair. Human hair is about 75 micron meter diameter. It depends on the people, or sometimes 50 or 100 micron, but normally it's 75 micron diameter. So other visible particle is 25 micron. The particle that we can see is 25 micron. And then we have floating dust, about 10 micron. Pollen atmosphere, dust about 5 to 10 micron. Bacteria, clear atmosphere. You see clear atmosphere, actually we have many floating particles, 1 to 5 micron size. Smoke, metal is about 1 to 3 micron. One particle, not a number of particles. One particle we cannot see. Particles emit from human body based on activity. So no matter how beautiful is your body, but you still emit particle because it's very small inside they cannot see. You thought that your body is very clean, nothing come out from your body. So depend on activity, the 0.3 micron size of particle emitted from your body, the standing or sitting activity is about 100,000 particles. Sitting with small movement, about 500,000 particles. Body and hand movement, 1 million particles. Stand up, 2.5 million particles. Slow walking with the speed of 3.2 km per hour, it's about 5 million particles in a minute. Normal walking, 7.5 million particles emitted from your body. And exercise movement greater than 8 km per hour is about 15 million particles emitted from your body in a minute. Classification of clean room. In industry where a specific level of cleanliness has been established, the federal standard STD 2.209E form is used. So this standard outlines the airborne particulate cleanliness classes. So class limit are given for each class name. So this limit designed specific concentration of airborne particle found in the clean room. So as you can see on the slide, the classification of clean room, the class 100, class 1000, class 10,000, 100,000. Yeah? Class 100, the number of 0.5 micron per cubic foot is about 100. It's easy. Yeah? 100 is 100. 1000, 1000, 0.5 micron particle per cubic foot. And 10,000, same, 10,000 particle. 100,000 is 100,000 particle. So this is easy to remember how we can classify the cleanliness of clean room. To compare the degree of cleanliness based on location, So you can see here, there's a number of 0.5 micron particle per cubic foot. In IC fabrication fab, normally 100, or some less, class 10 or class 1. In stratosphere at 40 kilometer above the sea level, that one is 200, class 200. It's very clean environment up there, so you can make fabrication process if you want, but we don't have the lab over there. So we don't have to make a clean room because the air is already clean. No? Number 3 is air and sea surface, about 80,000, class 80,000. And clean city, 5 million. And polluted city, 10 million. So you know where is a polluted city, where is a clean city. So Kuala Lumpur, for example, is clean city. So the number of particles is about 5 million particle per cubic foot. So clean room with class higher than 100 is called super clean room. So class 10 and class 1 was introduced metric system is used with class M1 to M7. So class M1 is for 10 particle per cubic meter and M7 10 million particle per cubic meter. So another metric system classification standard. So this slide just to want to show you the comparison classification based on US Federal Standard 209E. As you can see, so we have class name and in SI unit and also in English unit, and the number of particle and the particle size. You can refer to 0.5 micron particle size and see M1, how many? It's about 10. But class 1 in British system, you can see the number of particles also there. Um, for metric system, M1 is 10, but that one is equivalent to 0.28 particle in cubic foot. And M1.5 equivalent to class 1. So we have 1 particle per cubic foot, but actually 35 particle in cubic meter. So you can see this table to show you the comparison, because sometimes we use a metric system, sometimes we use British system. Particles distribution according to degree of cleanliness. For comparison, you can see the graph, the number of particle bilangan zarah versus particle size or size zarah in micron. For example, you take a particle with 4 micron. 4 micron in class 10, they have about 0.1. But in class 100, have about 1. And class 1000 is about 10. And class 10,000 is about 100. And you can see other particle, for example, 0.5 particle. The smallest one here is class 1, 1, class 10, 10, class 100, 100, class 1000, 1000. So you can see the based on the class of clean room, you can see how many particle exist in the clean room. So for example, about 30 micron particle size. 30 microparticle size is only exists in class 1000. It's about 0.1. And for class 10,000 is about 1. So you can see this is the distribution of particle to degree of cleanliness. So this slide shows the table with the clean room class. You can see class 100, class 10,000, class 1,000, 100, 10, and 1. And the particle size, you can see the particle size. And also the air velocity or maximum vibration per unit, and also the humidity, you can see. So temperature is controlled between 68 to 72 degree Fahrenheit, and humidity is controlled between 40 to 46 degree. So room is held positive pressure to blow dust out. So door is open inward. So when the room pressure will close them shut. So normally the clean room is door is open inward. Clean room elements. Both the design of a clean room and its operation must be set up to keep dirt and contamination from getting into the room from outside. So 9 techniques are used to keep out and control dirt. So there are adhesive floor mat, gowning area, air pressure, air shower, service bay, double door, pass-through box, static control, shoes cleaner, and glove cleaner. Layout for typical fab or processing area. So this slide shows the layout of clean room. You can see we have a prep area and then in the middle. Then we have a service area, service aisles, access to maintain equipment. So the technician can maintain the equipment from outside. And we have an air shower. We have the gowning area. So from the door we have a bench, and then you put a gown and then enter the room through the shower. And we have a pass box also, a pass-through box for chemical and also for semiconductor. So this slide just to show you the picture inside the clean room. You can see the corridor. Corridor is not process area, so the operator or workers can walk through this corridor. It's a clean, but it's not clean as in the fabrication process. And you see other picture also. The in the testing, it's not very clean, and also the wet process area. You can see the equipment, the fume hood, and the people working there in a processing or wet processor. A clean room structure. So the basic structure of advanced clean room is illustrated as shown in the slide. You can see that they have a 3 split layer. So the top layer is a AHU, air handling unit, and then the clean room, and then the bottom is the service area. So the airflow from the top to the bottom through perforated floor, and the workers and also the process equipment is inside the clean room. So the clean room usually has a raised floor with grid panel which allow airstream to flow vertically from the ceiling to the area underneath the process and equipment area. And airflow return to the clean room through the highly efficiency particulate air filter, call it HEPA, which remove most particle carried by the airflow. In building the clean room, because the cost is very high, to cut cost, only vapor processing area are designed with the highest class clean room, whereas equipment area have lower class clean room design, and most facilities are not in the clean room at all. For fabrication of IC chip with 0.18 micron, better than class 100, class 1 clean room is needed for the processing area. And normally class 1000 is good enough for the equipment area, which represent a significant saving in design and maintenance. So the equipment, the body of the equipment we can have in the not very clean area, but the process area have to be very, very clean. So it has to be class 1 or class 10, for example. But the class 1000 can be for the equipment or also for service. A clean room is always kept at higher pressure the non-clean area, so which keep airflow outward against airborne particle when door is open. Little bit higher, not too high pressure, little bit higher than outside or other non-clean area. So the same principle applies to the different class area inside the clean room. Because in the room we have clean room, we have clean room in the clean room. So higher class area have higher pressure than lower class area in the clean room. So variation in temperature, airflow rate, and humidity can also disturb surface particle. So all atmospheric must be strictly controlled in the clean room. So airflow into clean room are filtered using HEPA filter. HEPA means higher efficiency particulate air filter. So which is designed with efficiency of 99.97% to remove particle of 0.3 micron. Pressure in clean room is higher than normal room by 0.25 psi. We call it positive pressure also. Okay, this slide shows the HEPA filter, which you can see airflow direction from top to down. And now we have, because we need a high pressure to push the airflow through the filter. But now we have one filter with already built a fan, so we call it fan filter unit. So one HEPA filter come with the fan, so not just like this. So that is the present technology. Last time we depend on the pressure with the ASU to push down the air through the HEPA filter. So we'll continue with clean room structure. So to achieve better than class 100 cleanliness, it is important to keep a linear air flow, usually called laminar flow, and we have to avoid air turbulence. So air turbulence can render particles on the surface of the wall, ceiling, table, and tool or airborne and make it difficult for them to settle. So with laminar flow, airborne particles are carried away quickly by the airflow. So class 100 is the dividing line between laminar flow and turbulence flow. An important point with respect to clean room cost. So sometimes what determines us which class that we want, which flow type what we want is the cost also. So lower than class 100 can be achieved with turbulence flow and cost much less than laminar flow. To make a laminar flow is more expensive than just turbulence flow. So we have to think what we want to do with the clean room, whether it's we have to use laminar flow or not necessary. We can use turbulent flow also as long as we can achieve what we want. So airflow type, we have four airflow type for clean room. One is turbulence flow, vertical flow, in the airflow vertically, horizontal flow, the airflow is horizontal, and also conventional flow, just like normal aircon. So the slide shows the type of airflow in clean room. So the first left on top is the vertical flow, but the return air will flow through the wall. So if we don't have enough space to make perforated flow, so we can do that at the wall. We can have a filter so that the air flow vertically, and then at the bottom near the flow, they flow through the wall. The second one on the right is the actual clean room with perforated flow. The airflow from the HEPA filter vertically, and then the laminar air flow will go through perforated flow. Then at the bottom left, there is a horizontal flow. So the airflow through the HEPA filter from the side and flow horizontally to the other side of wall. And the fourth one is the conventional flow. So we have filter, HEPA filter on the ceiling. So the air return through the wall, only one side only. So this is the conventional. Then from the return, the air return will go back to the HEPA filter. Okay, air shower. So in clean room we have air shower. So what is air shower? What's the function of air shower? Air shower is to serve to protect your clean room environment from unwanted contamination. So clean garment, for example, become contaminated during the gowning or ungowning process, and because of high traffic in the gowning area, so the clean garment is contaminated already. So the contamination problem is amplified when the same garment is worn several times or is taken on off numerous times during the day. So when you enter the clean room with the garment, so we need to blow off the particle or contaminated on the garment. So air shower is a fast and effective method of removing the surface contamination. So the air shower is quality constructed using heavy gauge painted steel or no particle on board to minimize particle generation. So air showers are available in a variety of sizes and shapes to provide a cleaning system to meet your specific application at different clean room. So the slide shows the picture of air shower. You can see from the left the diagram how we enter the clean room through air shower. So first we open the door, and then we already in the shower, and the air will blow, and then after a few seconds, after 40 seconds for example, we can set the time, and the door inside the clean room will be open, and then you can enter the clean room. And the pictures show the picture some type of clean air shower. You can see the top is already in enter the clean room, and at the bottom is the picture of air shower that you can choose. There are many type of many shapes also. So apart from clean room itself, so in the clean room we want the work area, the place that we can do our work, cutting a sample or cutting a wafer or to clean a wafer and to do a chemical etch everything. So we have a laminar flow hood or LFH or and we have a wet station. So for laminar flow hood or LFH, the air from clean room will go through the filter, HEPA filter, and then you can do your work here, like cutting a sample, a wafer. So the air will blow, not blow, will pass through laminarly through facing your face. It's a clean to clean the sample wafer already. And then second one is a wet station, just like fume hood, but different fume hood. But here we have laminar flow of air from the top or from HEPA filter, and from the top will blow downward vertically, the laminar. So the work area where you do the process, everything is very clean, but at the same time, because you do chemical process, the air, the gas need to be sucked out from the clean room. So we have some velocity calculation, the air flow out and also vertically flow toward the sample. Okay, the slide shows you the view inside the clean room where they have a wet station where all the process or chemical process or wet process will do in this wet station. Okay, so this slide show the analysis which source of contamination in the clean room. You can see where the source is equipment, process, people, vapor handling, static charge, and also chemical purity. So which one is contribute more? For example, here equipment will contribute more than 30%, and then the process more than 25%. The people, the vapor handling, and charge, static charge, and so chemical purity. So the which uh, uh, component will contribute more on the vapor particulate. Okay, working in the clean room. So clean room operator are required to wear special non-linting bodysuit, overshoes, glove, head covering, and also mask. In some clean room, workers even pass through air blast upon entering the clean room to remove particle and to ensure minimal contamination of the environment. You can see the picture there, how it looks like when working in the clean room. Um, Gowning procedure. Some fab require people to put on linen glove before they even enter the gowning room. So the gloves are usually made of composite fiber that do not tend to attract particles. They can prevent sodium and particles on the hand from contaminating the clean room garment. Human hair becomes positively charged via friction, which attract negatively charged particles. Certain pressure, humidity, and temperature conditions discharge and neutralize these particles so they are no longer attracted by hair. So that's why we need to control the parameter, the pressure, humidity, and temperature also, because we want to minimize the charge also, particle from attract by the hair. So discharge particle from hair could easily become airborne and cause contamination. So hair cover block the emission of this particle. So they are among the first thing to put on in the gowning room. And men with beard are usually required to wear a beard cover. Beard are strongly discouraged in most IC fabrication. So the bottom of shoes carry the largest amount of particle. So many fab use sticky mat, or those or shoes brushes to remove dirt from the shoes before putting on the shoes cover. It is very important to keep bare shoes on the entrance side on the bench and cover shoes on the other side of the bench to prevent large amount of particle from being carried into the gowning area. So that is the function of bench. You see on the bench, put shoes, put cover on one side, and then the other side is the other part of bench. So and then if the one leg already covered, shoes already covered, and then you can put another leg. Okay, this slide shows the gowning procedure on for number one is intersuits needed for cleaners classes. Then we have a shoes cover, we have cap, we have a hood. After putting a cap, you put a hood. Then we have a face mask, and then coverall, and then boots, safety glasses, and also glove. And then complete, then you can enter uh, the air shower before entering the clean room. A clean room clothing, it depends on what type of what class of clean room. No? For example, class 1, you need all of this: hood, hair cover, coverall, intersuit, boot, facial cover, glove, and safety glasses. And then class 10, hood, hair cover, same class 1. Then you can see class 10,000, not many, not all you need to put. So you need to put at least frog, boot or footwear, special cover, glove or safety, that's all option. So depend on the class of clean room. So you can choose the clothes, the suitable clothes to enter the clean room and to work inside the clean room. Not necessary to have all type, for example, class 1 clothing, and then you work with class 10,000. Not necessary. Okay, this slide shows the governing area of clean room. So inside the governing area, you can see there are many gown rack, depending on how big is your clean room. We have benches. We have shower there, the air shower. Then we have storage to put all the clean room garment, everything. So the design of governing area depend on your clean room and also depend on what you want to put in the changing room. Factor determine vapor cleanliness. As already discussed previously, the source of contamination, but the four factor here to determine your cleanliness, your vapor cleanliness. So one is the operator, you're already inside the clean room. So operator, the environment is a clean room, the equipment, and also the chemical or gas that you use. So these four factor. Even though you're already working in the clean room with the good environment, good equipment, but the chemical and the gases that you use is not a clean room standard. So you cannot get a clean vapor or clean device that you want to fabricate. Okay, make sure the chemical and also the gas is also clean room standard. So here is some example calculation. So if we expose 200 millimeter vapor for 1 minute to an air stream under laminar flow at 30 meter per minute, the speed, how many particles will land on the vapor in a class 100 clean room? So the solution, the calculation, for class 100, there are 3,530 particles, 0.5 micron per cubic meter. You can refer to the chart. So the air volume that goes over the vapor in 1 minute is that one, 30 meter, the speed multiplied by the area, the vapor size, and also the time. So we get 0.3425 meter square. So the number of dust particle in the air volume is that one, the clean room, the particle in the clean room, the 3,530 multiplied by the 0.9424, and then we get 3,320 particle in the class 100. So in the class 10, for example, we can replace the one. So we get 332, and class 1 we get 30 particle. We settle on the wafer, 0.5 micron size of particle. Basic structure of IC fab. IC fab usually consists of office, facilities, storage, equipment, wafer processing, and chip testing and packaging area. So offices, facilities, and process material, storage, obviously not clean room. Wafer processing equipment, chip testing, and packaging take place only in the clean room. So wafer must remain in the processing area, which maintain the highest class of all the clean room. So most of process equipment is installed in lower class clean room. Sometimes it's called gray area. So the gray area interface with higher class clean room, so that wafer can be transferred into the clean room for processing. So chip test and packaging normally take place in even lower class clean room, since this process involves a much larger feature size, which is much less sensitive to particle contamination. So not necessary in the higher class clean room for testing and packaging. A semiconductor manufacturing process. Semiconductor manufacturing has many processes which classify under 4 basic operations. So this is the process. So we can classify into adding process, removing process, patterning, and also heating process. So doping, layer growth, and deposition area are adding process. When we add a layer, etch, clean, and polishing are removing process. Photolithography is the patterning process, and annealing or alloy and reflow are the heating process. So easy, we can divide it into 4 class of process for manufacturing, for semiconductor manufacturing. So wafer processing area usually are separated into several process bay. So they include wet bay, diffusion bay, photo bay, etch bay, implant bay, thin film bay, or CMP bay. So process engineer, process technician, and production operator works mainly in the process area. Process support engineer employed by equipment manufacturer also work mainly on this area, in this area during tool startup and when process troubleshooting after something happen. So the process support engineer will come normally from the manufacturer, and we have not many from the manufacturing itself, because we only need this engineer to maintain, not to do every day, to maintain the equipment. So normally from the manufacturer. So this show the example of process flow in wet processing area. So first thin film growth or the deposition or CMP. Then after deposition, we do photolithography for patterning. After we have the pattern, we can etch or we can implant, depend on the step. Then in the etching, so we have photoresist stripping to remove the resist. Also in implantation, we have photoresist stripping, and sometimes we need to do for RTA or rapid thermal annealing or deposition, and then return back to the position. So this is very general flow of semiconductor process. Okay. Normally in manufacturing, we have to use track stepper for integrated system. You can see here, to do patterning, we have wafer and then enter pre-deposition chamber, and then spin coater to coat wafer with resist, and then go to stepper for patterning, step and repeat, and then move, hot plate, then develop, and then after develop we cool down, and then we get the wafer with complete pattern on it. So this is manufacturing, not in the normal lab, like university lab, I think, because we only process 1 or 2 sample. This one we have 100 or 1,000 of wafers for the same process. So we can do this track stepper. Okay, this is the floor plan of semiconductor fab. Just example, but not necessarily like this. It depends on the design, but the concept is like this. So when we enter the gowning area, the clean room, then we have the corridor. We can enter many process bay. For example, we have the clean room is in the process bay. Then we have the equipment area is the gray area, and also the service area or sliding door, so that here we can enter to the process area, the clean room. So the maintenance engineer or technician, they can use this bay to maintain the equipment. Clean room do and don'ts. So this one is easy to remember what we can do, what we cannot do in the clean room. What we can do is we can change glove. We have to change glove whenever dirty or torn. Use a fresh pair of gloves whenever handling wafers. Wipe down wafer handling area with isopropanol. Use clean room paper and dust-free ball pen. Remove all ring and bracelet from fingers and wrists. Use special lint-free papers and pen or marker. And what we cannot do, don't touch your face or skin with glove. Don't touch oily machinery or hot element. Don't land on equipment. Don't wear cosmetic, powder or cologne. Don't use normal paper and pencil. So this easy to remember what we can do, what we cannot do. So do and don'ts in clean room. Okay. So if we have a complex, for example, E-Man building, for example. So in E-Man is not only clean room, we have the office for admin and for the staff, everything. So we have to separate a separation between admin, building, and clean room. So this shows it's not immense, but very similar to what we are doing. This one from somewhere. You can see the clean room block and also the staff block and also the admin. We separate. Anything happen in the admin that's not connected with the. So this is the picture of complex penyelidikan or research complex where we have a number of research institute, but the main institute is IMEN. You can see the one block there is IMEN future clean room. That block is belong to IMEN only, and then you can see very similar to the previous diagram. You can see we separate between the clean room area and also the admin or the office and staff here. Okay, in the process laboratory or chemical laboratory, the most important thing that we have to have water. So the water that we use in clean room, we call it deionized water or we call it DI water. So water or city water is pure enough to drink, but not necessarily is pure enough to be used in the clean room. The most prominent of contaminant found in water are in the form of ionized particles and gases. So ionized impurity are categorized into two groups. One we call it cation, carry a positive charge such as sodium, calcium, and magnesium. And anion carry a negative charge, chloride, sulfide, and bicarbonate. So how to remove the contaminants? So we can remove the contaminant through a series of chemical reactions. So this one take place as the water pass through the ion exchange resin. Deionization is actually the reverse exchange of unwanted ion from liquid phase for wanted ion from a solid phase or ion exchange resin. So this ion exchange resin can be specific for the removal of one particular ion or one group ion or removing anything and everything that is in charge. Cation resin is used to remove positively charged ion, and anion resin is to remove negatively charged ion. So first stage of filter is activated carbon used to separate chlorine, organic material, and bigger particle. So second stage of filter is to filter particles with sizes of greater than 10 micron. So dissolved material in water are separated by third stage filter through reverse osmosis, or people call it RO. So then water is deionized through force filter. For some systems, UV is used to control the bacteria. So finally, water passes through membrane to separate particle which is greater than 0.22 micron. So water quality is upgraded through the eye polisher and finally through 1 micron filter to separate residue from ion exchange and polisher. High purity water cannot be stored too long because it will be contaminated by particle or microorganism from container. So water exposed to air can absorb carbon dioxide molecule or gas or other gases. Therefore, pure water must be used direct immediately after purification process, meaning that we cannot keep the water in a bottle and then we use the next day or next week. We have to use directly, immediate from the tap. So that's why each clean room, normally all clean room, we need to have our own DI water system. Okay, this slide shows the DI water system as we already explained previously. You can see we have the first filter, activated carbon filter, and finally we produce 18.3 mega ohm centimeter resistivity of water. That means it is pure enough to be used in the clean room. So this diagram shows the how we produce the DI water system. As in our laboratory, we have this. So normally the purity of water, whether the water is pure enough to be used, so we can monitor the resistivity, because the resistivity will reflect the solid or the dissolved solid in the water. For example, 18 mega ohm centimeter resistivity. So the dissolved solid 0.0277 part per million. So this is good enough to be used in the clean room. So you see the lowest 10,000 equivalent to 50 part per million. No? So in the clean room, we cannot use water with the quality lower than 10 mega ohm centimeter, but normally we maintain it 18 mega ohm centimeter. Ultrasonic cleaning, this one to remove the particle stick on the surface, can be removed by transferring momentum to the particle. So the smaller the particle, more difficult to be removed and require higher momentum. So ultrasonic wave is used. So ultrasonic wave in liquid will cause compression and expansion in sinusoidal form. So sine wave with frequency greater than 16 kilohertz have high energy compared to audible sound wave. So we use this frequency normally for. Okay, this slide show you the picture of our DI water system, as we already explained in the diagram. But this is the real one. The picture when we install the DI water system when we start building the clean room last time. Just to want to share with you. So this is the DI water system at International Semiconductor Research Center at Seoul National University in Korea, in South Korea. You can see in the picture, Professor Junduk Lee. So he established the clean room in ISRC, and he was our visiting professor at IMAN in 2007. So he showed me the clean room and also the DI water system at the institute or at the center at Seoul National University in Korea. Okay, this slide just want to show you the clean room, our clean room in 1996 at UKM. So this is the first clean room and maybe first clean room in the country also. So you can see not many equipment in the lab, in the clean room. You can see we have two people working, our technician and my postmaster student from UITM, study masters under me at UKM. So not you can see not many equipment compared to what we have now. But this is 1996. Our clean room was established in 1995, and so not many. So this clean room is supported by Telecom Malaysia. So that's why we call it UKMTM Microfabrication Laboratories. During that time, it's not yet a center, just a laboratory. So.